Welcome to the second video lecture for Chapter 9. In the first lecture, we talked about some of the details of how stars function in general in terms of their pressures, the minimum maximum sizes of stars, and what size of stars are the most common. Now, in this second half of the chapter, and the slides for the chapter, I'm going to focus on the specific life stages of low-mass stars and high-mass stars. All right, so let's get to low-mass stars. All right, so our goal here is to learn what are the life stages of a low-mass star and how does a low-mass star die. All right, and in the next chapter, we'll learn about what happens after they die. All right, so what are the life stages? And this is showing the life stages of a dying low-mass star when it leaves the main sequence. Because remember, the main sequence is where stars spend most of their lives, and when they leave the main sequence, that means they are dying. All right, so a subgiant and a red giant are forms of a dying low-mass star, but we'll talk about that. All right, so a star remains on the main sequence, okay? That's where it changes hydrogen into helium as long as it can fuse hydrogen into helium in its core, okay? So what happens when a star can no longer fuse hydrogen to helium in its core? What do you think happens? Based on the ideas, all the principles that we introduced in the last video. The core shrinks and heats up. Why? Because nothing is there to push back against gravity. It was only the fusion pressure that was holding gravity at bay. Okay, so the life track after the main sequence. So for low-mass stars, all right, the observation of star clusters show that a star becomes larger, redder, and more luminous after its time on the main sequence. All right, notice, right? We're going up in luminosity, we're going down in surface temperature, which is the redder part, and we're going up in size. All right, so in other words, movement overall to the upper right, this direction, is meeting all of these criteria: larger, redder, and more luminous. All right, so this is when the thermostat breaks. And this is hearkening back to the idea of the thermostat of our own sun, this idea that there's this natural thermostat. Well, eventually it breaks because the fuel source runs out. So as the core contracts, hydrogen begins to fuse helium in a shell around the core. All right, because that contracting core is releasing a huge amount of energy because the gravitational potential energy is being turned to thermal energy. That thermal energy is then getting radiated through the shell around the core, thus heating up that shell, instigating its own fusion. All right, so here's the main sequence star, and here is the expanding red giant. And notice it has a hydrogen shell fusion. The luminosity increases because the core thermostat is broken. The increasing fusion rate in the shell does not stop the core from contracting. All right, so now there's just more energy being produced because there's a combination of fusion, probably less total fusion than there was before, but still fusion, and a lot of gravitational contraction. So all that energy has to go somewhere, and it goes into the luminosity of the surface, which now is greater. Okay, so helium fusion does not begin right away because it requires higher temperatures than hydrogen fusion. A larger charge leads to greater repulsion. And the reason we bring up helium fusion is because if you've been paying attention, you might think, oh, well, why doesn't the core just start burning helium? After all, the byproduct, so to speak, of the hydrogen fusion during the main sequence of the star was helium. And helium can get fused together to form, say, oxygen, right, or carbon. But why doesn't it? Okay, well, because it takes a lot higher temperature, simply put, okay? So what's going to happen first is the shell of hydrogen fusion around the collapsing core, and eventually that collapsing core then will become a helium fusion core, okay? So fusion of two helium nuclei doesn't work. It just because of nuclear forces, it just doesn't happen. So instead, helium fuses into carbon, which takes 3 helium, okay? So that's the process of helium fusion. It's quite interesting that you can't, for whatever reason, you can't get 2 helium together to form an oxygen. Instead, you get 3 helium together to form 1 carbon. So what happens in a low mass star when the core temperature rises enough for helium fusion to begin? Well, does the helium fusion slowly start? Does hydrogen fusion stop? Or does helium fusion rise very sharply? All right. Well, it rises really sharply. Because think about it, degeneracy pressure is the main form of pressure in the inert helium core, okay? And so at that point, it's been compressed a huge amount until suddenly the helium starts, and it's going to start rapidly because it's basically all that mass is then able to start fusing into carbon, all that helium mass. All right, This is this is the helium flash. That point where kind of the helium engine of the dying star, so to speak, well, the helium engine, so to speak, of the dying star, it suddenly starts going, and that's the helium flash. So the thermostat of a low-mass red giant is broken because the generosity pressure supports the core. The core temperature rises rapidly when the helium fusion begins, and the helium fusion rate skyrockets until the thermal pressure takes over and expands the core again. All right, because once it's less compact, then the fusion rate won't be so dramatic. So that core that's been collapsing will actually kind of fill back in, kind of filling in low density space within the center of the star. All right, so the helium burning stars neither shrink nor grow because the core thermostat is temporarily fixed. So the idea is that a star like our own, a low mass main sequence star, will go through this phase where it runs out of hydrogen, starts to die, starts to expand, starts to become a growing red giant, but then will then have a core that's shrunken enough to start helium fusion and then become a helium star. And for a while, it's almost like it's back to normal. It will actually shrink a bit again, not back to its original size. It will still be redder than it was before, but it will be not a main sequence star, but a fairly stable star. All right, but it won't last forever because the helium, there's just not as much of it, and that period will only last for a few million years or tens of millions of years, not nearly as long as the 10 billion years of which the star was able to burn hydrogen. All right, and burn, of course, is in quotes, I mean fuse, and that 10 billion is a universal number, but it applies to stars of our size of the sun. So models show that a red giant should shrink and become less luminous after helium fusion begins in its core. So it kind of returns to this stable-like phase. All right. And observation of star clusters agree with those models. The helium-burning stars are found in a horizontal branch of the HR diagram. Right, so they're right there, are all the helium-burning stars. So the combining models of stars of similar age but different mass helps us to age-date star clusters. All right. And right. So how does a low-mass star die? Because we got this idea that, okay, it runs out of hydrogen, it starts to expand, there's this whole collapsing core business, but then eventually the helium fusion kicks in, and now we've got kind of a stable helium star. But we're still edging towards death, all right? So what happens when the star's core runs out of helium? What do you think, right? Are we just going to keep fusing heavier elements, right? Well, next, helium starts fusing in a shell around the core. And that follows the same trend, because what happens when it ran out of hydrogen in the core? A shell of hydrogen fusion began around the core. But that means if a shell of helium fusion is beginning around the helium core, now that the helium core is out of helium, what happens to the core? Well, it must start collapsing again. So after the core helium fusion stops, the helium fuses into carbon in a shell around the carbon core. See, now it's a carbon core. And the hydrogen fuses to helium in a shell around the helium layer. So that's double shell burning, because now there's even more energy further out in the upper layers of the sun. We're still pretty far in the interior, but we are beyond the core. And so we now have these shells of burning hydrogen on the outside, helium on the inside, and collapsing carbon core at the very center. And the carbon is, after all, the byproduct of the helium fusion. This double shell burning stage never reaches equilibrium. The fusion rate periodically spikes upward in a series of thermal pushes. So now, pulses. So now the sun is really, really out of whack, all right, the star. And the star at this point will expand even more. And this is where it reaches full red giant status. This is where our particular sun will become so large that it will engulf Earth's orbit, by Earth, right? But we have 5 billion years until that happens, by the way, so plenty of time. So this is really the star in its final stages. With each spike, the convection dredges carbon up from the core and transports it to the surface. And by the way, the surface is so big and the star is so luminous at this point that the star starts losing significant amount of mass. It loses about 50% of its mass during this phase of double shell burning, because it just keeps the gas is so energetic that it's faster than the escape velocity of the gravitational pull on the surface of the star. And there's a mix of hydrogen and helium and even carbon that's been dredged up. And so all those elements are just kind of flying off into big clouds, plumes of material that's getting pushed down into space, creating a huge cloud in the solar system that before was not populated by a huge cloud. If you were, say, be on a moon of Saturn and kind of out of the range of the giant expanding red giant, the sun, because let's put this in perspective. If you're at Saturn right now in our own solar system, the sun just looks like a particularly bright star in the sky. It's really no brighter than, say, like Venus or Mars or Jupiter appear in our sky here on Earth. whereas of course the sun is incredibly bright for us. And so you're on that moon of Saturn. The sun is just particularly bright, the star in the sky. When the star reaches the red giant phase, it becomes noticeably brighter. All right, so now it really looks like something that's not just another star. But you wouldn't get engulfed by it, right? Because you are many millions of miles away. But what would happen is there would be all of this mass being shed off from the star, and it would eventually start to basically like cloud up the sky. So there would be like less and less visibility of stars in your sky from being a moon of Saturn, because there's just all this extra dust and gas in the solar system. All right, so that creates what's called the planetary nebula. All that gas that is getting shed off during this stage. So double shell burning ends with a pulse that ejects hydrogen and helium into space as a planetary nebula. The core left behind becomes a white dwarf. All right, and it's a gradual process. It's not one single pulse. But the planetary nebula is a terribly named, astronomical creation, because in reality it has nothing to do with planets. When the first ones were discovered, they looked circular like this, and astronomers thought 100 years ago that maybe they were planets, exoplanets, right? Now we know what exoplanets are actually like. They're nothing like this. And so the name stuck, however, so we still call them planetary nebula. But planetary nebula are the shedded upper gas from dying low mass stars. Again, the planet part of the name is completely a misnomer, all right? And it's basically just the gases being ejected from a low mass star. From the side view, you can clearly see that it's actually big plumes of gas, and here is the dying red giant at the center of those plumes of gas. All right? And that's the end of fusion. So the fusion progresses no further in a low mass star. All right? That carbon core that we mentioned, that's it. That carbon will never fuse in anything else. It is an inert carbon core. Okay? Inert carbon core. All right? The temperature just never grows hot enough to fuse heavier elements. All right? So helium fuses to carbon. Some helium fuses to carbon to make oxygen, but that's not much. That happens in really trace amounts. The degeneracy pressure supports the white dwarf because that's what's left behind. We'll talk about more of that in the next chapter, against gravity. So there is something left behind, and it's called a white dwarf. More on that later, but not in this chapter. Okay? So in summary, we've got a star like the sun starts to die, becomes redder, more luminous, and larger, becomes a subgiant, eventually becomes a giant. At this point, it has an outer shell of burning hydrogen, but that core is still collapsing. When that core finally starts fusing helium into carbon, it becomes a carbon star. That carbon star is stable for a while, but never truly stable, and gradually starts to fall apart, becoming even bigger into a double shell red giant. And that double shell red giant gradually sheds about 50% of its mass into a planetary nebula, and then what's left behind cools and becomes a white dwarf. That's the story of the life cycle of a dying low mass star. All right? So Earth's fate. So the sun's luminosity will rise to about 1,000 times its current level, too hot for life on Earth. Furthermore, the sun's radius will grow to near the current radius of Earth, well within the range that we'll experience gravitational friction from the sun on, our oceans if we have any left. And that means that we'll gradually slow in our orbit, which will kind of allow us to maybe escape being falling into the sun, but maybe we'll get bombarded by a big solar plume or solar flare of some sort, and then end up crashing into the sun. So even if the planet survives, it will barely survive. All right. So hydrogen fusion in the core, in summary, hydrogen fusion in the core is the main sequence by definition. When hydrogen fusion in the shell around the contracting core starts, you have what's called a red giant. Eventually, you have helium fusion in the core, which is a horizontal branch on the HR diagram. Then that's followed by double shell burning, which classifies as a red giant. After the low mass star has really finished with its double shell burning phase, it then ejects a bunch of helium into a planetary nebula, a mixture of helium and hydrogen and carbon, and then becomes an inert white dwarf, which gradually cools over billions of years. All right, but now let's do the same kind of thing, but let's do it for a high mass star, because high mass stars are quite different. They're 30 to 150 times bigger than the sun, and it turns out that some different physics apply. So what are the life stages of a high mass star? How do high mass stars make the elements necessary for life? And how does a high mass star die? All right. So here are the paths in the HR diagram we're going to discuss for high mass stars. Notice they're much more horizontal, right? Where the stars was kind of like this, right? Well, a star like the sun was like that. High mass stars, they go straight over. They just have basically a cooling surface temperature, very little change in luminosity. But why? All right. So first of all, high mass stars, when they're on the main sequence, are still on the main sequence and they still classify as hydrogen burning stars, but they don't actually go through the same fusion process. So instead of taking the 4 hydrogen, creating 1 helium, ejecting 2 hydrogen, a neutrino, a electron, and an anti-electron, and some light, they instead go through quite a bit of a different fusion process. And it's described by what's called the CNO cycle. And CNO stands for the fact that there is carbon, nitrogen, and oxygen in the process, right? Which is interesting because those are much heavier elements that we haven't really associated with main sequence stars before. But they were always around because these stars, after all, are second and third and fourth generation stars that are born from the matter of previous blown up stars that created those heavier elements in the first place. And so those elements are around, and there's enough of them in the high mass stars, and they're hot enough, and the core is hot enough in the high mass stars, so even though they're fusing hydrogen and helium, they're using catalysts, so to speak. Think in chemistry language. They're using these extra elements to create a more energetic cycle, the CNO cycle. So high mass main sequence stars fuse helium to hydrogen, or the hydrogen to helium, at a higher rate using carbon, nitrogen, and oxygen as catalysts. Greater core temperatures enables the hydrogen nuclei to overcome greater repulsions. All right? So it's, so the overall process is quite similar in terms of the inputs and the output, but the fact that we have these catalysts of oxygen, nitrogen, and carbon is unique to high mass stars. All right. So later life stages of high mass stars are similar to those of low mass stars. All right. So we have hydrogen core fusion, right, during the main sequence. Eventually, we run out of enough hydrogen, even though it's a CNO cycle, it's slightly different. Still, there's a finite amount of hydrogen in the core. After that, well, the core starts to collapse and hydrogen shell burning begins, right? So that part is basically the same, all right? And then eventually that core collapses enough for helium core fusion to begin, okay? Still, that's all, we've seen that before, okay? All right? Now, the thing is that high mass stars, they're able to have, because their core was bigger to begin with, and there's much more gravitational pressure pushing on that core, it's able to continue to heat up. Enough so that when all the helium fuses the carbon and the carbon core is left behind, it's not inert. It actually can continue to fuse. And we can make those heavier elements necessary for life. Because when you think of the building blocks of life, oxygen, nitrogen, and carbon are important. And carbon obviously is produced in low mass stars, but even things like magnesium are very important. All right? So the Big Bang was entirely hydrogen and helium. And it's good to appreciate that. I've said that before, but that is the case. There was simply no other elements. And we talked about those first generation stars, the ones that were really, really big and massive and unstable and only lasted for like 10,000 years. Well, those are the very first things that create heavier elements. Because before that, the universe was just hydrogen and helium, okay? The stars make everything else. Helium fusion can make carbon in low mass stars, and that carbon obviously is very important for life. And that's why carbon is so common, because both high mass stars and low mass stars make it. Okay? And that's why really carbon is the building block of life, because it better be, because it's what you have to build with. Okay? But what about all those other elements? All right? So the CNO cycle, that's the hydrogen to helium fusion rate of the high mass stars, can change carbon into nitrogen and oxygen. Excellent. Okay, so now we have the explanation of where nitrogen and oxygen come from. But what about other things, right? What about neon? All right? What about magnesium? All right? So the higher core temperatures allow helium to fuse with heavier elements. All right? So helium capture builds carbon into oxygen, neon, magnesium, and other elements. Right? So it comes from those cores of high mass stars, and this does not happen in low mass stars. All right? So the core temperatures in stars greater than 8 times the mass of the sun allow fusion of elements as heavy as iron. So all the way up to iron, right? So that would include, things even like, we have, chromium, we've got titanium, calcium, potassium. These are all being made in those heavier stars, those high mass stars. Argon, sulfur, that's a big one, right? Silicon is produced in the fusion. That actually gets produced quite a bit in one of the final stages of fusion, right? So everything up to iron, but iron is the end of the line, okay? So advanced reactions in stars can make elements like silicon, sulfur, calcium, all right, and iron. Okay, how so? Well, because something happens that's called multiple shell burning. It's a lot like the double shell burning in low mass stars, it's just more elements. All right? So we have advanced nuclear burning proceeds in a series of nested shells. All right? And the idea about the nested shells is that we would have on the very outside, we would have non-fusing hydrogen. Then we'd have hydrogen fusion, which has been kind of pushed out progressively because the star has been getting hotter and hotter. We have a helium layer, a helium shell, just like in low mass stars. Then we actually have a carbon shell instead of an inert carbon core. Inside of that, we have a shell of oxygen, neon, and magnesium. All right? And then we even have an inner shell of silicon fusion. And then we do have an inert core, which is iron. Right? But then why doesn't the iron fuse, right? Can't you have a star that's big enough that you just keep creating shells? Couldn't you go like all the way to uranium or something? Well, no, because it turns out that the periodic table has a rule. And it's a rule that says that iron is the bottom of a bowl of energy. Because here on the vertical axis is mass per nuclear particle. And here we're talking about protons and neutrons, the nucleons, the particles that build up the nucleus of atoms. And here on the horizontal axis is atomic mass, which is just the elemental numbers of elements, which also refers to the number of protons. Well, this is the number of protons plus neutrons inside the nucleus of the element. And so as we go from the lightest element on the periodic table, the lightest element in the universe, to hydrogen, up to the very heaviest naturally occurring element that we know of, uranium, we see that there is a bottom out at iron. It's the bottom of this bowl. And obviously it's much steeper on the side of the low mass elements, but it's still bowl shaped, see? All right? And that bowl is bottomed out at iron because iron is a dead end for fusion, because nuclear reactions involving iron do not release energy. Because the idea is if you fuse iron, you produce something that's heavier than iron. You could, for example, produce nickel or something, right? Or more likely, I mean, if you're fusing two things if you fuse 2 iron, you get 52. So actually what you would produce would be tellurium, right? Or you could maybe add an extra hydrogen in it and you get iodine or something. But the point is that if you did that, then you would end up losing energy. And so a star can't maintain energy and push back against gravity if it's fusing iron. It would actually help the collapse of gravity because they would be losing energy in the fusion of iron. And that actually happens. That's part of what's called the iron catastrophe for supernovas. They actually do. There's so much energy that the iron starts to fuse, but then that process then eats up more energy than it basically, there's more energy being consumed in the process than went into it, and so that speeds up the collapse, and there's a rapid collapse of the core, thus a huge explosion, and that's the supernova, all right? So, but again, the important idea is that iron is a unique element on the periodic table, a unique element in the universe, because the periodic table is just a reflection of reality, and because it has that special role to play, that its nucleons, the mass per nuclear particle, the mass per nucleon is lighter than any other element in the universe. All right? Iron is special. And that's actually even true if you were doing fission, it would be the same way. You can split apart uranium and get, lead or something, or, plutonium, and you can produce energy in that fission process, which is splitting, and you can continue to split apart elements until you split apart elements until you got the iron, because you can't split apart iron and get energy. So iron is neither useful for fusion nor fission. It can never produce energy because if it goes either way, it loses energy. All right, so fascinating. All right, so evidence for helium capture, higher abundances of elements with even numbers of protons. So if you look at the actual common nature of elements in the universe, some are more common than others. All right, so how does the high mass star die? Well, iron builds up in the core until the degeneracy pressure, remember that was electron degeneracy pressure, can no longer resist gravity. The core then suddenly collapses, creating a supernova explosion. All right? So that's the idea, is that the collapse of the high mass stars is dramatic and explosive and releases a huge amount of energy, whereas the death of low mass stars is gradual and creates the planetary nebula. So big difference there. Okay? And the supernova explosion occurs when the core degeneracy pressure goes away because the electrons combine with protons, making neutrons and neutrinos. The neutrons collapse to the center of forming a neutron star. All right? And we're going to talk about that in the next chapter. Because that's the idea, is that what the pressure, the quantum mechanical pressure that was holding stars together, the degeneracy pressure, the fact that 2 electrons cannot be in the same place at the same time, well, that's true unless the pressure is so great that the electrons can't push back anymore. And that actually causes them to be forced to become a neutron. So the electrons will actually push together with a nearby proton and become a neutron. You might be like, how is that even possible? Well, it turns out that it's all because of the wave nature of matter and something called the weak nuclear force that states that electrons and protons and neutrons are all kind of one and the same wave matter, and they can interchange between their different states. And in this case, the wave function of the electron, the wave function of the proton can become the wave function of the neutron. Okay? So energy in neutrons released in supernova explosions enable elements heavier than iron to form, including gold and uranium, because when that huge explosion happens, it actually creates fission because there's so much energy. It's like a nuclear bomb, and it can then split apart elements and then recombine them into heavier elements. Okay? So the energy released by the collapse of the core drives the star's outer layers into space. That creates big nebula, such as the Crab Nebula, which are supernova remnants. So that's one particular type of nebula that exists in the universe, supernova remnants. And they're characteristic because they have a rapidly accelerating outer edge, and they leave a particularly low density bubble inside. And it turns out that research in the last 10 years has shown that Earth currently is passing through the bubble of a supernova remnant that occurred about 200,000 years ago. Not that long ago, right? All right, so the closest supernova in the last 4 centuries was seen in 1987. All right, and we can see how bright it is. All right, the supernova's flash of light caused rings of gas around the supernova to glow. All right, and more recent observations show that the inner ring is lighting up debris that crashes into it. Okay, so in summary, what are the life stages of a high mass star? They're similar to the life stages of a low mass star up until a point, but then high mass stars are able to create heavier elements that they produce in their core, and they produce even heavier elements in the supernova itself. All right, so there you have it, a summary of low mass star life cycle and high mass star life cycle. Some similarities, but also some important differences. And the final product of both of those types of stars are different. Low mass stars become white dwarfs. High mass stars become neutron stars or black holes. And that's what we're going to discuss in Chapter 10. All right, well, thank you so much for watching this video. I hope it's been interesting and informative.